This video will be about hybrid orbitals, orbital overlap, and sigma and pi bonds. As an unbound atom, carbon has 2 electrons in 1s, 2 electrons in 2s, and 2 electrons in 2p. However, carbon rarely exists as a single atom and is usually found with its valence electrons, the electrons in the outer shell, bonded to other atoms. When carbon makes 4 single bonds, its electrons are seen to be at equivalent energy levels, so the s and p orbitals need to hybridize so they are all at the same energy level. Because the energy of the electrons has changed, the shape of the orbitals also changes. In this scenario, the hybrid orbitals are called sp3 orbitals. The s comes from the 1s orbital that contributed to the hybrid, and the p3 comes from the 3p orbitals that contributed to the hybrid. Because each orbital is equivalent, they repel each other with equal force, producing equal bond angles. Remember, an electron has a negative charge, so electrons will repel each other if close together. This explains the VSEPR model, which you will meet in the Shapes of Molecules section of these tutorials. Each sp3 orbital only contains one unpaired electron, allowing carbon to bond to 4 atoms. Here, we show methane, where the carbon is bonded to 4 hydrogen atoms. Both the hybridized carbon and hydrogen atoms have unpaired electrons, so bonding allows them to pair and exist at a lower potential energy. These bonds occur due to the overlapping of the hybridized orbitals of carbon and the s orbital of hydrogen. These single bonds arising from the end-to-end overlap of orbitals are called sigma bonds. What about double bonds? We're going to use ethene to understand how double bonds are formed. We know the single bonds are sigma bonds, and the double bond also contains one sigma bond, but it also contains a pi bond. Let's see how hybridization explains this. Pi bonds are formed by the sideways overlap of unhybridized p orbitals. This means there needs to be a leftover p orbital after hybridization. Therefore, only 2 p orbitals are involved in hybridization in this case. These orbitals are called sp2, as one s orbital and 2 p orbitals have contributed to the hybridized orbital. These sp2 orbitals are found on a plane perpendicular to the unhybridized p orbital. Let's look now at the formation of the double bond. Here are 2 sp2 hybridized carbon atoms. Firstly, sp2 orbitals from each carbon atom overlap to form a sigma bond. The pi bond then forms due to the sideways overlap of the unhybridized p orbitals, forming a single pi bond which spans above and below the sigma bond. The remaining 4 sp2 orbitals are able to bond with 4 hydrogen atoms to complete the ethene molecule. Now let's look at the hybridization in triple bonds, using ethine as our example. In this case, the CH bonds are sigma bonds, and the triple bond contains 1 sigma bond and 2 pi bonds. In order to create 2 pi bonds, we need 2 unhybridized p orbitals in each carbon. Let's look at the hybridization. For clarity, the 2 unhybridized p orbitals are different colours, a light green and a dark green, to make the bond formation easier to see. After hybridization, we end up with 2 sp orbitals and 2 unhybridized p orbitals. The notation sp comes from the 1s orbital and 1p orbital which have contributed to the hybridized orbitals. The other carbon in ethine has the same hybridization, so let's look at the formation of the triple bond. The sigma bond forms from the end-to-end overlap of sp orbitals. The darker p orbitals overlap to create the first pi bond. The lighter p orbitals overlap to create the second pi bond. We can see here that the pi bonds lie on separate planes which are perpendicular to each other. Finally, the hydrogen atoms will bond with the remaining sp orbitals to complete the ethine molecule.